Our first talk will be given by Anitha Gollamudi, and we're going to hear about the MS-Wasm project. Please take it away.
Thanks, Benjamin. Hi, everyone. I'm Anitha, and today I'm going to present about how to safely compile unsafe code using WebAssembly. And this is a project with all these excellent collaborators. Okay, so first, a brief primer on WebAssembly. WebAssembly, or Wasm, it's a new bytecode language that is meant to run native apps at native speeds and safely. It's across various platforms such as web, edge, and cloud. And then the majority, it is designed as a portable compilation target, and a majority of the code, Wasm code that is in existence today, has been compiled from high-level languages such as C, C++, and Rust. The cool thing about Wasm is that it's already adopted in industry, and it is hugely gaining in popularity. It's present in all major web browsers, in Cloud, Azure, Nginx, as well as in Docker. Wasm is pretty attractive because of its focus. One of the reasons why Wasm is attractive is because of its focus on safety. By construction, Wasm code runs in a sandbox. And what this means is that if there are two co-tenants, say Alice and Bob, that's running their Wasm modules in a cloud, they get isolation for free. And this is pretty cool. However, within the sandbox, there's very little protection. If you compile a memory-unsafe program, it still remains memory-unsafe at the Wasm level. So if you compile a memory-unsafe program such as C or C++ or Rust, by that I mean the unsafe portion of the Rust, the vulnerabilities persist across the compilation. And these vulnerabilities can perform unsafe actions such as leaking secrets via buffer overflows, or even could bypass the sandbox. So in order to set like a concrete example, let's take the classic memcopy from the C library, which copies source to destination for a len number of bytes and compile it to Wasm. So as you know, that len doesn't have any relation between with the destination buffer. This could lead to a buffer overflow in memcopy. And when it's compiled to Wasm, you don't have to read the code shown on the right, but the vulnerability persists. The reason is that Wasm uses a linear memory to lay out the data structures. And so the source and destination buffers are laid out as bags or sequences of bytes. And moreover, the pointers are compiled as integers. And thereby, we are losing all high-level information or critical information, such as length of the buffers. And therefore, the characters are copied to destination byte by byte. And the load stores do not have any information whether it's happening within the bounds of a buffer or beyond, which leads to the classic buffer overflow vulnerability. So what can we do about this? One strawman approach is that I could probably instrument the C source code and with safety checks, such as checking for the bounds of the buffers whenever there is a load or store. And then what happens is with the compilation, these get transformed into inline memory safety checks at the Wasm level. In fact, the research work such as Southbound, Sets, and Secure adopt this approach. However, there are at least 3 limitations with this approach. What's wrong? First, there's no robustness, which means that if you have a Wasm module compiled with inline safety checks, and when you have to link it against another module that also has inline checks, so that you get the memory safety as a whole, which means that this could prevent you from linking with, say, a third-party library that's, say, not compiled with these defensive checks. The second reason is the source code instrumentation, these inline memory safety checks means that we're committing to a single memory safety policy much ahead in the compilation. Say, for example, spatial memory safety, which is about buffer overflows. And this limits the progressive enforcement of memory safety policies. So what do I mean by that? Not all applications require full power of memory safety. So depending on the performance security trade-offs, they might implement, they might require only, say, spatial memory safety or temporal memory safety, or maybe some form of handle integrity, pointer integrity. And so depending on the timeline, they might start with like a partial implementation, and over a period of time, they might just convert into full memory safety. But because of these inline memory safety checks, we lose the flexibility to adopt such a gradual or progressive approach for enforcing memory safety. And last but not the least, the most important thing is these checks are slow. Why? One of the reasons why these checks are slow is because they cannot leverage the hardware performance. So emerging security architectures such as ARM, Spark, and Cherry, they provide hardware features for efficient enforcement of memory safety. And because we are compiling because the Wasm code gets compiled with inline safety checks, by the time we are at the Wasm level, we are losing the high-level information of these data structures. And recall that because Wasm treats pointers as integers, we can no longer leverage these platform-specific features for efficient enforcement. So what's our solution? A solution is MS-Wasm, or a memory-safe variant of Wasm, which extends Wasm with memory safety abstractions. It brings first-class memory safety features at Wasm level. And it does so using 3 key features. The first one, in addition to the linear memory that I have introduced earlier, it introduces segmented memory, which is a collection of segments, and each segment should be thought of as a bounded region of memory. With the feature that a segment can only be accessed by a handle. A handle is an unforgeable pointer with some metadata that tracks the memory safetiness of pointer operations. So I want you to know that theoretically, segments are distinguished by colors. And this is a theoretical tool, and the implementation could be different. But what this means is that if you're familiar with the pointer provenance work, the segments serve the colors serve the same purpose of tracking the pointer provenance. I'll get back to the notion of color again in later slides. And also note that the handles are very similar to Fed pointers, except that the handle here is now an abstraction, and it gives the developers the flexibility to choose the right implementation. So for example, they might choose to have only spatial memory safety, and so the handles store information only necessarily required for that, for enforcing that. And then the third feature is that these MS-Wasm abstractions enable compilers to enforce memory safety robustly, progressively, and efficiently by leveraging hardware. So in the rest of this talk, I'm going to talk in more detail about the MS-Wasm design and how a compilation from, say, C-to-MSWasm enforces memory safety along with its formal results, as well as the implementation insights. So first, as I mentioned, MS-Wasm supports segments and handles, and then it also supports new instructions for accessing these segments. So first, how does one create a segment? This is similar to malloc in C. So using a seg-alloc instruction, we get back a segmented memory, as well as a handle pointing to the base of the segment. And notice that both the color of the segment and the handle is the same, they match. The intuition for this is that the handle is allowed to operate only within the bounds of that blue segment. And so if you're using other segments, seg-alloc instructions, you get back other segments, but each segment has a unique color. Okay, great. So now we have handle pointing to the base of the segment. So we want to move it around so that we can do some pointer arithmetic. And so handle add instruction, which takes another integer offset, it increments or it moves handle in either directions. So here I'm saying like move the handle by 12, and so it moves the handle beyond its segment. Notice that the color of the segment that the handle is now pointing to it has a different color. So it's pink or orange, some shade of red with blue. The point to note here is that this is always a legal operation. It always succeeds. So, and this could represent an out-of-bounds pointer. The interesting part is like, how do we access segments? So now we know that the segment, the handle is pointing to a different segment than it was originally created to point to. And so the accessing a segment is done using seg load store instructions, which are similar to load store instructions, and then they succeed if the colors match. But now we have a situation where the colors are mismatched, and so this could potentially represent accessing an out-of-bounds location, and therefore the instruction traps before it performs any load store. So this is the key insight why a buffer overflow or vulnerability such as buffer overflow could be prevented. So for more details, I urge you to refer to the paper which described the formal semantics. So great. Now that I have shown you MS-Wasm primitives, I'm going to show you and hopefully convince you that it is a good compilation target for enforcing memory safety. So you must have already had the intuition by now that our formal C-to-MSWasm compiler, the way it compiles C code is by because there is a natural mapping between the allocation of segments as well as accessing segments. So it maps malloc to segalloc and pointer dereference and pointer storing to seg load store operations as well as pointer arithmetic to handle add. So using this, I want to revisit the buffer overflow vulnerability that I have shown to exist or persist at Wasm level. So recall that there's a buffer overflow when we are writing beyond the destination buffer at the Wasm level. But if you're compiling the same code, same C code to MS-Wasm, the way it works is that instead of the regular alloc and load store, we generate these new instructions, seg alloc and seg load store, as well as a handle of add operation for manipulating the arithmetic, pointer arithmetic. So the first instruction, seg alloc, gives us, say, a blue segment, which is allocated for a destination buffer, as well as a handle to that. And what happens later on is that using the handle add, we're tweaking the offsets, and now we come to a point where the handle is pointing to out of the segments that it was originally created to. At this point, seg store traps because there is a color mismatch because the handle is pointing to a segment that has a different color. And thus, the buffer overflow is prevented. Hence, the MS-Wasm programs are memory safe. But what is memory safety formally? So our definition of memory safety utilizes a monitor that consumes a trace, a program trace, which comes from program execution, and that a trace of memory events, interesting memory events such as allocation and load stores. And then this monitor steps on each event by inspecting whether the colors match within an event or not. So concretely, so we have MS-Wasm events, seg alloc, seg load store, that are fed to the monitor. So if the colors match, the monitor steps successfully, otherwise it gets stuck. And MS-Wasm program is memory safe if the trace that's consumed by the monitor is terminated successfully without getting stuck. If it gets stuck, there's a memory safety violation. Otherwise, it's a memory safe execution. Note that this monitor is not a runtime monitor. It's just a theoretical tool to define the memory safety. Okay, just let's recall to one of the limitations of the inlined memory safety checks, which is the lack of robustness. So what is robustness here? So we have a well-typed MS-Wasm program that we are now linking with a library that's produced by a different compiler. Now the robustness here means that if the composition is memory safe or not. And we have a formal result which says that any well-typed MS-Wasm module is robustly memory safe, which means that an MS-Wasm module linked against any other attacker module, the resulting traces are memory safe. Okay, great. So we have robustness. And so, but how do we prove our formal C-to-MSWasm compiler enforces memory safety? So recall our monitor, which we have used to define which we have used to define memory safetiness for MS-Wasm programs. We now generalize it and make it language independent by lifting the memory events to abstract events. And then we lift an MS-Wasm program trace to this abstract trace and feed it to the monitor. If it gets stuck, there is a violation, otherwise it's safe. And the cool thing is, we can use the same infrastructure to reason about the memory safetiness of a C program by mapping the relevant memory-based events to these abstract events. And this is our proof setup, and this is key for our proof in that it gives us a cross-language equivalence relation, which is necessary to establish the soundness of a compile-based memory safety enforcement. So what we have proved in our formal compiler, our C-to-MSWasm compiler is of course type preserving. It takes a simplified subset of C. Particularly, this simplified C allows attacks or vulnerabilities such as buffer overflows, and it compiles to MSWasm. Our key theorem is that this formal compiler enforces memory safe execution of unsafe code. What this means is that we break it down into two cases. So suppose we are compiling a well-typed and a memory-safe C code, then the compiled code, compiled MS-Wasm code is memory-safe. And of course, it also preserves the semantics of C. It's not a dumb compiler. The second case is that we're now compiling well-typed but memory-unsafe C code, which means it has vulnerabilities. Even in that case, the compiled MS-Wasm program is memory safe in the sense that it traps at the first memory safety violation. Great, so that's the end of the formal story. And now I'm going to talk about the actual implementation in the last 5 minutes. More importantly, I'm going to answer the question on whether MS-Wasm memory safety abstractions enable the compiler to leverage the platform-specific features. So in our implementation, the compilation pipeline, there are two stages. The first one is the C-to-MSWasm compiler, which is based on the cherry fork of the Clang LLVM compiler. Specifically, it modifies the fat pointer implementation in the cherry fork to emit handles. The second part of the compilation pipeline is the actual compiler to compile MS-Wasm. We have 3 different compilers, one RWasm, Cherry SH, and DrawVM. And then the reason why we have 3 different compilers is because we want to explore various MS policies, memory safety policies, with different compilation techniques, say ahead of time or the JET, as well as different enforcement mechanisms, whether hardware or software-based ones. So our evaluation uses PolyBenchC test suites. It has a lot of insights, but our evaluation is not full and it is still a work in progress. And here I'm only showing you the highlights of evaluation necessary to address the question on whether the platform-specific features can be leveraged or not. And the answer is yes. So the key insights are that our RWasm compiler, which compiles MS-Wasm to Rust, it uses a software enforcement, specifically baggy bounds, to implement spatial memory safety. And any enforcement of memory safety incurs some performance cost, and our performance overhead against, say, vanilla Wasm is 21%. The Cherry SH, which uses hardware features, which is hardware capabilities to implement spatial memory safety and handle integrity. And the performance overhead against native cherry code is about 52%. Our final compiler is a GraalVM, which is a JIT compiler. It uses JVM objects to implement spatial and temporal memory safety. And the question we ask here is that whether a JIT compiler is slower than ahead of time compiler, and the answer is yes, and then the overhead is about 42%. Well, note that all three compilers are non-optimizing. And so our goal is to understand whether the hardware features can be leveraged, but not necessarily build an optimizing compiler. However, the numbers are encouraging in the sense that we can take advantage of full compiler optimizations to get performance numbers, which we leave it to our future work. Also note that each of the compiler is enforcing a different memory safety policy, which is attesting to the fact that MSWasm abstractions enable compiler for progressive enforcement of memory safety. So with that, in summary, what I have shown you so far is an MSWasm design which says that well-typed MSWasm programs are robustly memory safe, and a compiler that enforces memory safe execution of unsafe code, as well as compilers, as well as an implementation that shows the flexibility of implementing an MSWasm compiler for leveraging platform-specific features. So thank you.
Questions?
Hey there, great talk. I'm Josh from Cornell. So the story about safety, even in the presence of composition with untrusted code, seemed a little bit incomplete. Like, it seemed like a very strong claim. So, I mean, it's not possible, surely, that all memory safety violations are avoided, even in composition with untrusted code. So is it like memory safety over buffers created by the trusted code, or just does the trusted code, like, what are the boundaries here?
So the boundaries here are that the code is any well-typed MSWasm code. As long as it's well-typed, then we know that the composition is robustly memory safe.
So if you just compiled a hello world in MSWasm and linked it with some terrible unsafe code, you'd prevent all of the memory safety violations?
It should be a MSWasm code again. It should not be a WASM code. So the story is not about composing MSWasm code with the WASM code, which we throw up hands against because it's still memory unsafe. But then if you link it with another MSWasm code, there's no way that the attack works because any out of bounds access is prevented. So the access still happens, but it's just that it's a trap, and therefore you cannot actually do the load or store successfully. So to kind of paraphrase that, you cannot leak secrets. So you might be able to override, you might try to override to something and or access an out of bounds thing to leak secrets, but the operation will not succeed as long as it's an MSWasm code.
This is Ralph from ETH Zurich. I was wondering, so you mentioned memory allocation, load and store. Does this support deallocation? Like detect
yes, we do have free as well. Yes, and it gives a temporal safety.
And can I, related question, can I store these handles in memory?
So for the implementation, yes, but they have to be, so the way our implementation works is that the handle is out of bounds for any accessible region, which means that if there is a sandbox, and then we store handles outside the sandbox, but it is stored in memory.
No, I was wondering, can I, in my MSWasm program, take a handle, store the memory, and later load it again? Because that sounds like it would, then it becomes very hard to ensure that its integrity is preserved.
Oh, I see. So handle is now accessed as a data, and you're storing. I'll have to think about that. But the thing is, there is a feature called handle integrity. If this is a software-only enforcement, we throw up our hands in the sense that it now becomes an attacker-forged handle. But in hardware-based implementation, something like a cherry, this is not possible because they can only change few bits of the they cannot change any bits of the handle. So it depends on the kind of enforcement.
All right, we should go on to the next talk, I'm afraid.
Okay.
Thank you very much.